Okay, today we're going to talk about aluminum and gas elimination, also some things on aluminum metallurgy. So this is something you're going to be doing in class, in the lab, and so I just need to get you up to speed on it. It's also found in the Asplin notes or the course handouts I gave you on PDF and which are on the Canvas site, as well as I gave you actually a hard copy of this. It's the notepad copies here. So let's start it. Okay, so generally aluminum melts at, this is all degrees Celsius, but you can do a quick conversion in your head if you just double it. So somewhere around, it's actually around 1050 or so, but it's a little bit higher for pure aluminum. So 1100 something. So that's the liquidus temperature. Remember that liquidus means that that's when it, so liquidus is when it completely melts, okay? As it's cooling, it first hits the liquidus line, then it hits the solidus line, okay? So if you haven't had the metallurgy class yet, you wouldn't have seen too many phase diagrams or anything like that. So we'll talk about them a little bit, and if you have questions, please ask me when we have our little discussion before class next time. So very low temperatures, so you can use fine sand, get a good surface finish. You can cast aluminum in almost any process. Investment casting, sand casting, centrifugal casting, all these processes can be done with aluminum. So it's probably one of the most versatile metals out there. One of the problems, though, it is turbulent sensitive. In other words, if we slosh it around, and I've talked about this a little bit before, it forms oxides. It talks about this in your the book from Campbell, the mini casting handbook. In the very beginning, it talks about how turbulent sensitive alloys will get oxide layers mixed in with them. Risering, and we'll talk about that later, but it's a little bit of a challenge. Remember that riser is an extra reservoir of metal that feeds the casting during solidification. Its strength's about 7%. The big problem here is that because aluminum has such a good thermal conductivity, that it actually transmits heat very well through it. So what happens is, what you want to have to make a casting be, have porosity and stuff, you want it to be kind of cold on one end and hot on the other end, okay? And so if it's got good thermal conductivity, it wants to level that back out. So aluminum struggles from that standpoint too. It's just like when you try to, when you try to weld aluminum, if you don't have enough heat input, like a really intense heat input, what happens is the whole plate will get hot, and then eventually the whole plate melts instead of just the edge of the plate where you're trying to weld. So it's about kind of like the opposite of that. Medium long freezing range in sand casting alloys. What does that mean? That means it starts freezing at the distance between the liquidus and solidus. In other words, it starts freezing at, let's say, 1200 degrees or something like that, or 1050 or something, or 1150, and then it finishes at 1050. Okay, so there's 100 degrees when it's kind of in the solid and liquid. It's kind of partially, it's kind of mushy, or if you're talking about like ice, it would be similar to slush, where you have liquid and solid present at the same time. Also, because it has a low density, that means that there's not a lot of pressure at the bottom of the mold in order to fill the mold. So there's some challenges when you're dealing with aluminum. Okay, so in order to get a good casting with aluminum, we might need to get rid of we need to flux it. Well, what is fluxing? We want to try to avoid it if we can, but it kind of, you put some chemicals in the metal and it kind of sticks things together. It makes the metal better some way or another. There's a bunch of different types of fluxes you use. Degassing eliminates the hydrogen gas, and we did a whole lab on that. Okay, we might actually add gas with potatoes in order to offset some shrinkage in the casting. And we might do things like control the grain size of aluminum. Now, grain size is kind of harkens back to what we talked about in Intro to Metals, where fine grain things, like, in other words, metals are crystalline, right? So it's made up of lots of little crystals. And I can show you some microstructures later on in this lecture here. But so these little crystals form during solidification, okay? The coarser those are, the lower the mechanical properties. The finer they are, the better the mechanical properties. So you might want to put some special chemicals in there that make it have a finer grain just by adding those chemicals in there, or nuclei we call them. And then we might do things like modification of the microstructure. What does that mean? Well, we're trying to make it stronger, and we'll explain. Also, when we do use high silicon alloys, like as in, I don't know if anyone ever heard of the Vega engine. Vega was a car. Maybe I can segue to that in a second here. But the Vega was a car that they tried to use a die-cast engine block without cylinder liners. Now, people like BMW and certain other companies have done that, and it's been Porsche. It's been somewhat successful, but you have to have really good quality control. General Motors tried to do that in the 70s, and they didn't have the quality control that they do nowadays, and it was a disaster. They had to replace some of these engine blocks after about 20,000 miles. So if you're into muscle cars, a Vega is a really good car to put a V8 in. Real lightweight. Okay, so we can use fluxes to clean up the metal. Usually there's some type of chloride, and we put these in there. Now, chlorine is bad, so we want to make sure we have really good ventilation. And they've come up with better fluxes probably since these slides came out. But they're still, first of all, you have to buy them, and secondly, you have to maybe dispose of the kind of the skimmings in a different way if they're nasty fluxes. So some of the fluxes you might put on, you put a protective coating on the surface in order to keep the hydrogen away from it, and then also to keep the oxides off the surface or mixing back in, especially if you're using like an induction furnace or something like that. If you're using alloys with magnesium, that helps to have magnesium will form as it circulates, little atoms of magnesium as they come near the surface, they form magnesium oxides, and then you lose it from the alloy. So in other words, they preferentially form an oxide, forms on the surface, and then you'll lose that magnesium in the alloy, which is an important element. Okay, so agglomerating fluxes are nice because you kind of stir them in, and they help to, if there's little oxides and stuff in there, it sticks them all together so that they can either float up or sink to the bottom. Usually they float to the surface. Then you can skim them off. Okay. A lot of times the oxides, as you know from looking at the Campbell thing, they neither float nor sink. They kind of float around the middle of the metal. So we want to try to agglomerate those together if possible. Also, after you melt, you skim off that dross off the surface, and there's a whole bunch of metal trapped in that dross usually. So you can put kind of it's usually something that's like kind of exothermic, creates some heat. So you put the dross in there, and it kind of heats it up again. and some of the metal will ooze out the bottom of it. They have like a little separating, like a tray for doing that. We don't do that on our side, but someone has to. Otherwise, you have to, the dross that you scoop off, you send that back to the company that makes the aluminum, and they can recycle that. There's a fair amount of aluminum in it. So we're mostly going to use the agglomeration type. How else can we clean the metal up? You can, so if we melt in an induction furnace, the induction furnace we have, and I may have mentioned this, it magnetically stirs the metal. And so if you, I think I had you look over the molten metal the other night, and so you saw it made a big bubble on the surface, and the metal is stirring around in there very quickly. And so what happens is that means you form oxides at the surface, they make it drawn down inside the metal. So it's not a good program for melting aluminum. Why do we do it? Because we have an induction furnace. Although now we do have a resistance furnace. The induction furnace is a lot faster at melting. So if we don't have a lot of time, or if we need to keep up with a certain production rate, we can't do that in the kiln furnace that we built. So we might melt in the induction furnace and then degas in that new furnace we did. Maybe hold it. Hopefully some of those oxides will float out or whatever. Okay, you can melt in it. It just takes a really long time. So in industry, what we do is we use a reverberatory type furnace, which is essentially a big, almost like looks like a swimming pool, or resistance furnace. So you have essentially what we have in the lab, a kiln with a crucible in the middle of it. They're just bigger in industry, okay? And then they don't lift off like that. They just stay put. So induction melting is bad because of the stirring. We can put a filter in the melt handling process. In other words, a lot of times, when they're trying to transport metal around a facility, what they'll do is they'll have a big trough, might be 50 or 100 feet long, to go from one area to another area. And so it comes out of the furnace. This trough is heated by resistance heaters elements. And then as it flows through, you might have some filters. And a filter is just a ceramic foam. Here's one here. And so it's a ceramic foam. And when the metal flows through it, little particles of oxides and stuff get filtered out. And so they can make big sheets of this stuff. So you can have it on one side of the furnace and have the metal kind of flow through it to get to the other side of the furnace. Or you could run it through this launder where there's little filters in it or something like that. So you could filter it and degas it, and you're really going to improve the quality of the metal. Also, when you're actually pouring molten metal or something like that, you can use a ladle that takes the metal from the bottom. This is a teapot, and if you've ever seen a teapot, the teapot has, the metal would come from the bottom and then come up and out the spout, and the oxides stay on the surface, and you're taking clean metal from the bottom. They're a pain in the butt to keep clean, though, because that area down there that goes underneath it, it's kind of hard to clean out anything that gets stuck in there. Okay, let's see here. So how do we get rid of gas? Oxide and nitrogen don't really dissolve in aluminum, okay? Although oxygen does make aluminum oxide, which is kind of, it really wants to do that. So aluminum really wants to be aluminum oxide. So it says the free energy of formation is exceptionally low. What that means is it wants to form aluminum oxide. Hydrogen is very soluble, but as we at room temperature, or when it becomes solid, it has almost no solubility for hydrogen. So what happens is as it goes from liquid to solid, all the hydrogen gas wants to come out and form porosity. Also, the water vapor in the air, so this chemical reaction shows the water vapor in the air plus the aluminum at the surface goes to this Al2O3, that's the oxides that are bad that are floating around in the metal, and hydrogen, which the underline there means it's dissolved. Okay, so that's the reaction it wants to do. If there's any water vapor in the air, that's what happens. Okay. It's kind of got a little bit cut off, but it says solubility of hydrogen and aluminum is at 1 atmosphere of hydrogen. Now, we never have 1 atmosphere of hydrogen. Okay, I mean, there's only like some parts per million of hydrogen in the atmosphere, and it's in water vapor. Okay, so it really comes down to the humidity. So how humid is it out, and how much are we stirring the metal around? But this just basically shows you that at somewhere around 1200, this is where it solidifies. It basically, solubility goes to almost 0. Okay, but as you heat the metal up, the solubility goes up too. And this is logarithmic. So when we're in lab, we might want to try degassing at a slightly lower temperature. The problem is, though, if we're going to pour, we want to pour at like 1350, well, we have to be at 1400 then in order to pour at 1350, because when you take it out, it cools down and all that kind of stuff. So just so you know what a partial pressure is. Let's say, you know, in the atmosphere we have the atmospheric pressure, you know, 1 bar or whatever of atmospheric pressure. It's made up of air, which is oxygen and nitrogen, right? But it's also made up of very small amounts of, I don't know, helium and hydrogen and all kinds of other water vapor. Actually, a fair amount dissolves in it. But there's small parts per million of other elements, and they call that a partial pressure, because even though, you know, it said 14 psi for atmospheric pressure, but it's really like 13 point something, and then a small amount of pressure is coming from the argon that's in the air and stuff like that. Very small numbers, okay? But that's what the word partial pressure means, and you're going to need to kind of know that in a second here, because we're going to talk about this Sievert's law here. So essentially, the amount of hydrogen that dissolves into something at equilibrium, now doesn't always get to equilibrium, but is equal to some constant, so like a fudge factor that tells you how much, and then the partial pressure of hydrogen to the one, you know, the square root of the partial pressure of hydrogen. Okay. Some of the equations on these slides get kind of messed up, so I'll point those out. It's usually when there's a square root or something like that. So the problem is this constant K increases with temperature. So that's what I was talking about before. This last graph on the last page, as the temperature increases, this K increases, so the amount of hydrogen that dissolves in the liquid goes up. Okay. So if we have a high hydrogen content, in other words, a lot of water vapor, and a high temperature, then we're going to have problems. Okay. So how do we get rid of that that hydrogen? One of the ways is actually to put it in a vacuum, which we kind of actually did in the lab, but we weren't trying to degas it. But if you kept it liquid the whole time it was under a vacuum, that's one way you could degas the metal actually relatively quickly. Okay, so but you would have to have some sort of vacuum chamber completely around that melting area. It's possible, could be done, but that's really not very practical, okay, to be able to do that in a foundry application. So the next thing is degassing tablets. Now, we didn't try any of these because they're really smelly and bad. They also mess up the furnace. The chlorine will screw up the stainless steel on the outside of the furnace. The one in Madison's all corroded from doing this. But what you do is you essentially take these little tablets. They're about 2 inches. It looks just like this thing here, about that size. Okay, so the tablet. Now this tablet will do like a whole big ladle full of metal. So we only need we break this in a quarter, let's say, for our little furnace, and then we take that quarter chunk. Very careful with gloves and all that kind of stuff because it's pretty nasty stuff. And then we have like a little bell with holes in it. And then we take that and we plunge it. Of course, we're going to take that bell, we're going to preheat it, and we're going to shot blast it. Or somehow wire brush it, get all the rust off of it. And then we're going to put that down, drop that piece on top of the molten aluminum, and you plunge it below the surface, bubble, 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 bubble. And then it's degassed relatively quickly, like in a couple minutes. So we need to figure out our efficiencies are very low in what we're doing. So I'm kind of scratching my head a little bit. I think we need to make a new degasser head design. Okay. The results from this last go around seem to be pretty dismal as far as how fast we can get the gas out. So we can take inert gases like argon or nitrogen, and we can bubble them through the molten metal. And what happens is the bubble, as it's traveling up through the molten metal, it has a very low concentration of hydrogen in that. So it wants to go into the bubble, the hydrogen, because it wants to go from an area of high concentration to low concentration. So if we make lots of little bitty small bubbles and they're equally distributed going up very well, like we're trying to do with that rotary thing, it should take out the hydrogen, and it does. I just noticed that it's kind of slow. So we can use a lance, which is basically just a tube with like a ceramic tube, and goes blub blub blub, and they're pretty big bubbles. It doesn't work very fast. We can use a porous ceramic plug, which are really hard to get, but it's essentially the same thing as one of those filters. And so you're just basically, it's like if you ever had little fish, they have that little filter thing, they blow air through and all these little bubbles come off of it. So it's very similar to that. It just diffuses the bubbles smaller. And we can use the SNIF, or spinning nozzle inert flotation method, which is what we're doing. Okay, so rotary degasser is another word for that. But the gases we can use chlorine gas through the rotary degasser. We can use nitrogen, argon, or a mixture of two. A lot of times people use nitrogen and chlorine or argon and chlorine. That works really fast. So I think that's part of the deal, is that I think the chlorine works a little bit faster because there's some sort of chemical reaction going on there as well. Okay, so let's look at some. So this graph here shows you that as the bubbles get smaller, the efficiency goes way up. Okay, so this is bubble diameter centimeters. So that if we can get the bubbles like 1/10 of a centimeter, so a millimeter in diameter, it gets really efficient. Even 2 millimeters is pretty good. Okay, and that's about where we have those bubbles when we're doing our degassing. Is I can see these little bubbles pin pricking up through the surface. You want little pin pricks for bubbles. Okay, here is a commercial unit where we have molten metal coming in from one side here, going through 2 rotary degassers, so it stays in here for a certain amount of time. There's probably a filter right here, or it just said these are just baffles. Sometimes there's a filter inside here. And then the molten metal comes out and it goes to the casting area. Okay. So here's some data. This is alloy 319, and it doesn't tell you what temperature they're degassing at. Okay. I know that if you degas at a falling temperature, like if you somehow could control the temperature cooling rate, it will degas faster because you're giving it an incentive to because as the solubility of hydrogen goes down, it wants to kick it out anyway. So if you have bubbles there, it just encourages the hydrogen to go into those bubbles even more. Okay, but again, once you get it down to a certain temperature, and I got to pick it back up to this temperature over here in order to pour. You've got to put a cover flux or something on it because it's going to pick up hydrogen again when you're sitting around waiting for it to heat back up. So I'm a little bit. It says it's closer to 10 minutes with the Lance method. If you look at our stuff, it might even be longer than that. And they're getting a pretty high density, 2.7. Now, 319 has a slightly different density because it's got more copper and some other stuff in it. So we got to figure out what the deal is there, why it's taking so long. Okay, so you use this formula in lab. So the density is equal to the dry weight over the dry minus the suspended weight. Okay, so on the top you have the mass. On the bottom you have the mass minus the basically this is the buoyancy force, which is equal to the volume. So it's mass over volume. Okay. So we did this. We put a small little cup there. We put it in the vacuum. It formed bubbles, and those bubbles don't have a chance to escape because it can't get off the surface. So you basically do a density test on it. So what we're going to do is we're going to cut these in half with the bandsaw, sand them, and then this is lightly sanded and cut in half, sanded, and lightly sandblasted to permit a visual rating the amount of hydrogen in the metal. I think they sandblast it in order to cut down on any metal that's kind of smeared over the small little bubbles. You can also use a certain kind of file to do that. So here's a little chart. It shows you, when you cut it in half, what each density looks like. This is for 356 aluminum, which is what we're using. So remember that the alloy that we're using in lab is 356 aluminum. Okay, so yeah, so if you have a density of 2.68, it looks like this. I think we had 2.63. So we're somewhere between these two, but pretty on the good side. And then I think we had like 2.3 or something like that. Yeah, 2.3. So maybe something like this one, these two down here, somewhere in there. Okay. And then you can kind of, if you don't have one of these reduced pressure testers, you just cut it in half and compare it to this chart, and it gives you an idea of what it should, what your density actually is. Okay, so so the vacuum test tells you generally how much hydrogen is in there, but in a real casting, you're not going to see that much porosity, okay, because you're augmenting what's going to really happen. Okay. If you have a slower cool casting, you're going to see more porosity than you will in rapidly cool casting. So generally, with aluminum, the faster you cool it, the better the mechanical properties are, the better everything is. Okay. Okay. So if we have pores in our casting, it's going to reduce the mechanical properties because you got an area where there's no metal. Okay, so it's not going to be able to withstand any force. The gas, or hydrogen gas that formed the bubble, has no strength. So essentially, as we increase the gas content and we increase the porosity percentage, the ultimate tensile strength comes down, and so does the yield strength. Okay. And by the way, just so you give an idea of how strong aluminum is, these are thousands of pounds per square inch. So like you might have something like 35,000 pounds per square inch would be the ultimate tensile strength. And then 28, 29 would be the yield strength. Okay. And aluminum typically doesn't have very good elongation. Like 3% maybe would be what you'd get in industry. Okay, so as you try to flow the molten metal into the casting, the fluidity you're gonna lose fluidity as you put hydrogen in there. Okay, so if you have a really gassy metal, you might not fill the casting out. So you need to have a higher superheat. In other words, more heat in the. This is a fluidity spiral. So they basically they poured the molten metal comes in the center and it spirals out, and they just measure the length of the tube that the length of flow that it had, and it's in inches usually. So this is the fluidity in inches, and so as we increase the temperature, of course, we increase the fluidity. Okay, but it's hard to see which one is here, but the dirty 319 is this one here. Okay, the 319 that has been degassed is over here on the right. So it has a higher fluidity when you have no gas in it or little gas in it. So if you're making castings that you're trying to offset shrinkage. In other words, we have a relatively thick section, and your company just needs the outside to look good. They really don't care about some porosity on the inside. They're not going to machine in there or anything. So you might have some porosity in the center of this casting, but if your customer doesn't care or doesn't ask, then you don't care so much. But what you want to do is make sure you do have that porosity in the casting, because it can offset shrinkage. So as we go to too low of a gas level, this is the scrap percentage. So the scrap percentage goes up because now we have shrinkage scrap. And then as we go to higher gas content levels, the shrinkage goes down. The shrinkage scrap goes down. But as we keep on going, eventually we get gas porosity that's going to cause a problem. You get big holes in your casting. I remember spending I was working for a company that made castings for Ford. So we were making intake manifolds, and they had a bunch sent back from Ford because there's this one little feature on the intake manifold that they drilled, they machined it, and they opened a little pore, and it was right where an O-ring would go. And so there's two things can happen. You can tear the O-ring because there's a sharp edge there where you're cutting the side of a pore. And the other thing is, if that pore is right where the O-ring sits, right? So, your O-ring is here and it's sitting on that pore, and you open that pore up, the fluid can go around it. Okay? So it's a bad deal. So they I think it was on the injectors. I'm trying to remember. I think it was not sequential. The injectors were in the manifold, and so it wasn't a good deal. So I sorted, 10,000 castings because we had a little bit too much porosity in it. Where it ended up, they had a specification. It had to be a certain size. or below, and not in some area. Okay, so this is a phase diagram. Okay, what is it, if you haven't seen one of these before, is that as we increase, this is aluminum and then silicon. So silicon is a major component in aluminum. So as we go to higher percentages of silicon, which is along this axis here, and then temperatures along this axis. So this is a ratio between aluminum and silicon. Obviously, if we're at 20% silicon, we're at 80% aluminum. Okay, and so we never go really above 20% silicon. There is a couple alloys that are around 20%, but we never go above that. So the whole right-hand side of this chart can be thrown away to some extent. So what happens? So sand cast, permanent mold alloys are hypoeutectic. Now we did actually look at the iron carbon phase diagram a little bit, and there's a reaction that looks kind of like this. There is actually one that is right in the middle of that iron carbon phase diagram. It's called the eutectic. So you have a liquid goes to alpha and beta. Beta is way over on this side. And so alpha is on this side and beta is on this side. And so we have alpha and beta in the middle. So if we have a 6% or something like that, this is 10. So we have 6% alloy. We would heat up here. It would first start forming liquid, and then it would be completely liquid. And then as we cooled, it would come back down. So you really can't change the composition of that metal so much. So you go up and down on a single line, okay? So hypoeutectoid, or sorry, hypoeutectic. This is eutectic, not eutectoid. Eutectic has to do with liquid, and eutectoid has to do with solids, okay? So we're dealing with a eutectic here. Another example would be lead and tin. Lead and tin form a eutectic right around 50% actually. And it melts at a much lower temperature. You see, if I would have had 40% silicon, this is going to be 1,000 degrees C that would melt. Okay? And then if I'm down here, it's just 600 degrees C. So you can see that the temperature at which it melts is determined by what the composition is. Okay? So, so there might be other elements in here though, and you can't really account for the silicon and magnesium and the copper. Otherwise the phase the diagram gets to be like 5D, and there's no such thing. Anyway, so that eutectic thing's pretty important. We're going to talk about it in a minute. Okay, so how do we control the microstructure in aluminum? Now, aluminum's pretty simple, and in the past you just cast the stuff and assumed that it worked. Okay? But we can do some things that improve the mechanical properties. If we're making some, jet airplane parts or something like that, we got to get the thing as strong as possible. So we might do something called grain refinement. Okay, we might do something called modification, and then if we have a high silicon alloy, you might do something called hardening or refinement. This is really pretty tricky, this part right here, okay? But essentially what we're doing is, let's think of it this way. I don't know if you ever heard this, but they tried to make it rain in some places of the world, and the way they would do that is they'd fly up in the sky and they would, with airplanes, and they would throw nuclei into the clouds. Nuclei, I don't even know what they used, but they're little particles. Excuse me. It could be dust particles, something like that. And the water droplets actually nucleate. So if every raindrop that falls out of the sky was nucleated on some speck of dust or something like that. Okay? Because in the cloud there, it doesn't want to form a droplet. It takes a lot of energy to form a droplet. It doesn't want to do it. So if you give it something to form on, it does it a lot easier. If you ever did like seed crystals for, or for science, where you put a seed crystal and it grows on the crystal, or you did rock, what's it, rock candy or sugar candy or whatever it is, where you put little strings or something, hung them in there to make rock candy. Okay, so what I'm going to show you now is something that all I'm talking about here is, as I cool, if I put a thermocouple, a little probe into molten metal, and I let it cool, it's going to kind of cool and get down to a certain temperature, and then it might heat up a little bit again and then cool down a little bit. And why? Because in order to form the little grains, the crystals of solid, it takes some energy. So it sometimes will do something called undercooling. But when you add a grain refiner, some little foo-foo dust that you put in there that the crystals can form on, then the cooling curve looks more flat up here. Okay? I'm going to talk about that later. So this is an actual plot of temperature versus time. The metal is cooling down to some sort of aluminum, and it gets to some temperature here, and then it heats back up a little bit, then it falls down again, and it heats back up a little bit, and it falls down again. What's going on here is, first you have your liquidus. You hit the liquidus temperature. So let's go back up and look at the phase diagram. The liquidus temperature would be this top line here, because this is all liquid in this region. So as we're cooling, we hit this top line, okay? And then what happens? And then it cools, then it cools down a little bit, then it hits another bump, okay? What's that other bump? That other bump is this line right here. They just call it the eutectic, but it's this temperature right here, which occurs at 577. Okay? So if we go back here, now this is a different alloy. This is 319, that was 356, I think. Or remember that when you add like 3 or 4 other alloying elements, it's not going to follow that phase diagram exactly. Okay? So this is a quality control method, and if they see these things moving around here, it means it has an effect on what the microstructure is going to be. So here is what okay, so if we took a sample of aluminum, we polished it smooth, and usually you don't even need to hit it with acid or anything. You just look at it on the microscope, and what you're seeing is the silicon, the beta phase, on that phase diagram. Okay, so this is the silicon, the primary silicon that comes out, and then the white areas are primary aluminum. Okay, so little did you know, it's not, when it becomes solid, it's not a completely homogeneous structure. In other words, it's not all mixed up anymore. When it's a liquid, it's all mixed, but when you cool it slowly, things can separate a little bit. So sand cast, they separate a lot. And by the way, these little blobs are one crystal. Okay, so you see a blob, it's like part of a crystal. Okay, if you cast it very quickly, it cools very quickly, you get a much finer structure. These are all the same scale here. So this might be a die cast part. Okay. This is really important because this structure here, when I put stress on it, it's going to fracture very, very easily. Okay? This one's a little bit better, and that one's even better. So under the microscope, if we take and we etch away all the aluminum, this is what those little plates look like. They look like little plates, right? But they're in 3D. They're actually, sharp little plates. And so this is not great for mechanical properties. What happens is you put stress on this, and it's going to crack along these little plates. It's kind of like cast iron almost. Okay? So how can we improve that? What we can do is we can add something called, we can modify it. What will we do? We put sodium or strontium in the metal. And what that does is it somehow modifies the way that the metal solidifies so that the edges of those silicon plates that are forming are rounded. So that's going to be much better microstructure. These could both be the same exact metal. All you did was you added some strontium. How do we know that? I don't know. They did some research a long time ago and they figured it out. This is kind of a tricky chart, but generally, as we go to the top of the chart, okay, so here's the phase diagram showing the eutectic at just around 12 something percent, okay? So if I cool faster, hold on a sec here. Yeah. As I go to the bottom of this graph, I'm cooling faster, okay? And what happens is you get finer and finer microstructures. It says dendrites and silicon rods. Dendrites and silicon plates, large silicon plates. So we just saw on the microstructure 2 slides ago that if we cool really slowly, like in sand casting, we're going to get these large silicon plates. And by the way, so if I take, this is, let's say, 7%. That's what 356 is. And I go up and I'm solidifying really slowly, I'm going to have large silicon plates. If I'm going to solidify a little faster at 100 micrometers per second, like 100 microns per second, that's the velocity of the solidification. So let's say you got one side you're casting here, one side over here, and the solidification front, one of them's moving towards the other one, right? And it's kind of the rate at which that's moving, okay? It doesn't move super fast, so that's why the numbers are so weird, okay? So hopefully you understand this. Faster cooling rates, composition, and so if we cool really fast, we're going to have, instead of large plates, we have silicon rods. So the shape of a rod is much better than a plate from the standpoint of mechanical properties because they don't disrupt. You know, it's like the cornflakes in milk kind of analogy I used for cast iron. Okay. Okay, so modification, what it does is it just changes the shape of this silicon, the silicon structure, okay? So we use strontium, sodium, and antimony. I've never seen anyone using antimony. We used to use sodium. It's a pain in the ass because sodium is dangerous, and so they used to pack it in little aluminum containers in a vacuum, okay? I think I still have some of them somewhere. Strontium is not quite as reactive, but still needs to be stored in an aluminum container. Okay, so there's some theory here on what's actually happening and why modification works, why we can round the edges of those things. Why does it work? Okay, and some of these things they don't know for sure, but it says rod-shaped silicon grows at high rates caused by large undercoolings. That means this basically it's cooling fast. Okay, the modifying agents poison the normal nuclei that cause silicon phase to grow. The nuclei that normally does it is an Al3 phosphorus. So normally the nuclei, the little points that form, are this phosphorus aluminum alloy. The problem is that must be a flat plate, so it grows as a flat plate instead of a rod. Okay? So the modifying agents kill off the phosphorus, permit large undercoolings to occur so that we don't form big plates, we form nice rounded structures. Okay. Strontium is non-reactive, it's easier to add. Sodium, it's very reactive and then it fades. In other words, you add it to the molten metal and then you only have a certain amount of time to pour that molten metal, otherwise it will just fade away. And antimony and calcium are not common in the United States. I've never seen it used. Okay, so I just showed you this before. The thermal analysis can give us an idea of what's going on for a hypoeutectic alloy. Okay, that's what we already saw this. Okay, so hypereutectic alloys means above the 12%. So let's go back to that phase diagram-y thing. Okay, and you see above 12.6% or around 12%, it's going to go liquid, beta and liquid, and then alpha and beta. And so, get back down to it. What happens is primary silicon starts to form. And it forms these big, large blocks, which are great for wear resistance, like in an engine block. Okay. The other thing is, these alloys, the high silicon alloys, have a more similar coefficient of thermal expansion than does cast iron. So if you're making a head for a car where the head is aluminum and the block is cast iron, it will match the expansion and contraction more evenly. Okay, a few more slides here. So how do we refine the primary silicon? This is just talking. This slide is talking about hypereutectic alloys and why they're good or bad or whatever. Okay, so some things that are good about hypereutectic alloys: high strength, hardness, and wear resistant. Low coefficient of thermal expansion. Like I said, it's compatible with cast irons. And some bad things about it: it's hard to cast because it's got a long freezing range. And it doesn't feed over a long distance, which means that a riser is not very effective. It has poor machinability, poor surface finish even after machining. What happens is these chunks of the hard particles get ripped out of the surface. And then you can also have gravity separation. The silicon actually can float out. So this is what it kind of looks when you get it refined. Okay, nice little blocks like this. And this is what the piston was supposed to ride up and down. The piston ring was supposed to ride up and down on in those Vega engines. Okay, these are very hard particles, and then they have even some other hard particles around the outside of them. Okay. So adding phosphorus produces nuclei for silicon. The phosphorus normally add in the form of copper phos. Cu15, it's a 15% phosphorus and copper. We want to create 0.01 to 0.05% phosphorus in the liquid. Okay, unfortunately, this keeps the eutectic from being modified. So in other words, you can't get that nice rounded shape that you do on the other one. You don't really, you don't have the ability to have both. So, what's an intermetallic compound? An intermetallic compound is an element. Well, it's a compound that forms between two elements, and it can form between, let's say, copper and aluminum. It makes an intermetallic compound. They're usually very hard, and they're very bad for mechanical properties generally. So let's see what we got next here. So, one of the big bad actors is iron. So when you're die casting things, you're casting in a steel die. Sometimes you use metal tools, iron tools, to skim or do all kinds of stuff in the bath. Sometimes people even melt in a big pot of It's made out of cast iron. The foundry that I worked at is a die-cast shop. They melted in this big cast iron pot, and if the metal got held in there, it would be high in iron, and it was a bad deal. I think we used to worry about it. It says more than about 0.5%. I think we worried about it a little bit higher than that, but like 0.7 or something like that. But it makes these, it's hard to see here, but there's these like gray, really sharp things sticking here. It looks like it's a error on here, okay? So they're like needles. That's a problem. That is going to make really bad mechanical properties. So iron is a bad actor. Here's some more here. These little wisps that you see form it's like a crack waiting to happen, okay? And you can also get it in this Chinese script if there's some manganese in there as well. So aluminum is pretty complicated. Aluminum, silicon, iron, and manganese can combine to make this quote-unquote Chinese script type defect. Okay, once you're done with the casting of this alloy, you might need to heat treat it. And so most aluminums are pretty soft and not very strong as cast. So what are you going to do? So we're going to do a solution treat, and an aging is typically what we do. So we're going to take and we're going to heat the aluminum. Okay, you might see something like T6 is what they might say. So it takes a really long time. So it's solution treat, quench, then artificially aged. Okay, most aluminums have gone through this process, but it's for casting. Sometimes it's 10 to 12 hours in order to get all the silicon. In this case, it is magnesium and silicon. Yeah. So we have to soak it for like 10 to 12 hours just under the temperature that it starts melting at. And then we quench it in water or heated water. And then after you quench it in water, you put it in another furnace at a lower temperature and do something called aging. Okay? So then you get, it might be like 3 or 4 hours at 315 degrees. So anytime you heat aluminum above 315 degrees, you're going to screw it up. Okay? In fact, anything above the boiling point of water typically will start to screw aluminum up. Okay? So in your engine block, if you're starting to overheat, or your head, you're starting to overheat certain areas, that's bad news. You're going to start softening the metal. The aluminum silicon alloys must contain magnesium or copper in order to be age hardenable. Okay, so those are the active ingredients. And that is everything I have to say about aluminum. Okay, so some of that stuff was a little bit outside your comfort zone, but please read the book that I gave you. And then there's some other stuff that I didn't really assign for background reading, kind of towards the beginning of it. I can't remember what page this is on, but it's later in the book, the aluminum chapters. I don't have it in front of me. So read through this in the book, watch this, and then now you have a good basis for doing your lab on melting.